This is your presenter Asloob Mudassar, and I am presenting slide number 103 of the course on laser physics. Question is, find expressions for threshold pump power for the 4 and quasi 3 level laser systems. The answer is, in an ideal 4-level laser system, pumping process transfers the active medium particles to level 4, which decay immediately to level 3, which is the upper laser level, whereas the lower laser level, that is the level number 2, is almost empty. The upper laser level may be considered as consisting of many strongly coupled sub-levels, with the total population equal to N3. The threshold value corresponding to this level is given by. So the threshold value corresponding to level number 3, which is the upper laser level in a 4-level laser system, the threshold value for that level, that is for the level number 3, is written as N3 for a threshold value for N3 is equal to gamma over sigma E into L, where sigma E is the effective stimulated emission cross section. So and L is the length of the active medium rod. So what is gamma? Gamma is actually the logarithmic cavity loss, which we have defined earlier and is reproduced in appendix for quick reference. So the logarithmic cavity loss gamma is equal to log of R1 into R2 multiplied by the square of 1 minus Ti, where R1 and R2 are the power reflectivities of the mirrors and Ti is the fractional internal loss per pass due to all possible losses. Intensity is reduced by a factor of 1 minus Ti in a single pass and by a factor of 1 minus Ti square in a double pass. So gamma is the logarithmic cavity loss. And in one of the previous slides, for example, this is taken from equation number 84.10. That is from the slide number 84, where we have mentioned, where we have first introduced the value of gamma written over here. So for that one, you need to consult slide number 84 if you want to see further detail about the value of gamma and the cavity losses. So we have written the value of N3, the threshold value for the N3, which is the upper laser level in a 4-level laser system. We have written that value as given in equation number 1, which is equal to gamma over sigma E into L. Now gamma is the logarithmic cavity loss, sigma E is the effective stimulated emission cross section, and L is the length of the active medium rod. So equation 1 is valid when the pump rate Rp and the field, which can be written as absolute square of U, are spatially independent. For that one, you can see slide number 11 or question number 11 and slide number 13 or question number 13 for detail on this. That is for the detail on pump rate. So this equation is valid for the pump rate Rp when the pump rate Rp and the field, which is written as absolute square of U, are spatially independent. So here spatially independent is more important word. Including space dependence, equation number 1 can be written as. So you see that equation 1 was written for space independent case, but if we are considering a space dependent case, then we need to write down the average value of the N3 threshold. So the average value of N3 threshold is equal to gamma over sigma E into L, where the effective population of this level is defined as So we can define N3 over here as, that is the average value of N3 is equal to the integral over A. A is actually the active medium rod, or the volume of the active medium rod. So the subscript with the integral A stands for the volume of the active medium rod. A stands for active. So the integral over the active, over the volume of the active medium rod contains N3 into absolute square of u into dv divided by the integral of A containing absolute square of u into dv. So you see that the average value of N3 is calculated in this way. And you know that N3 is the upper laser level in a quasi, in a 4-level laser system. The integrals are evaluated over the volume of the active medium under the threshold pumping rate Rp, which is the threshold pumping rate in our case. The number of active medium particles moving to the upper laser level is the same as the number of excited particles decaying to the lower laser level. Thus, we can write that the pump rate can be written as, which is now the threshold pumping rate, because when we define the threshold pumping rate, we consider this point, that the number of active medium particles moving to the upper laser level is the same as the number of excited particles decaying to the lower laser level. So under that condition, the pumping is defined as threshold pumping rate Rp. So Rp is given by the threshold value of N3 divided by tau, where tau is the effective lifetime of level 3. For spatially dependent case, the equation number 4 can be written as, so we need to consider now the average values when we are talking about the spatially dependent, because you see that the spatially dependent means that we have to take into account the average value of these quantities. That is the average value of N3, threshold value of N3, and the average value of threshold of the pump rate. So the equation number 4 is now written as in terms of the average values. That is the average value of the threshold pump rate is equal to the average value of N3 population in the level number 3 divided by tau. Now we can eliminate, we have two expressions for the value of N3. One is given by equation number 5, the other is given by equation number 2, because we have N3 there in both equations. So we can eliminate N3 equation from equation number 2 and equation number 5, and we can write the pump rate, the threshold value for the pump rate for the space dependent case is, that is the threshold value for the pump rate. The average value of the threshold value for the pump rate is equal to gamma over sigma E into L into tau. This is the critical or the threshold pumping rate. Now you see that we are going to towards the longitudinal case. For longitudinal pumping rate with electrical pump power can be replaced by the threshold pump power from equation number 12 can be written as. So you see that in the equation number 12 we had the expression for the electric pump power. Now we are going to reproduce this expression for when we replace replacing the electric pump power by the threshold pump value. So PE replaced by P thermal, not P threshold, not thermal. So we are going to do that one using equation number. You see that here I have mentioned equation number 12 from slide number 102. So you can, for detail you can consult this slide. So you see that now I have written that the average value of the pump rate, that is the threshold value, for, that the average threshold value of the pump rate is equal to eta P into P threshold divided by H nu P, where nu P is actually the pump frequency. That is the monochromatic light that we are using in the pumping mechanism is the frequency nu P, and multiplied by 2 divided by pi into W naught square plus WP square, and this whole multiplied by L. So you see that W naught is the beam waste of the pump beam, because we are illuminating the pump beam longitudinally. This is the longitudinal case. It means that we are illuminating the active medium rod from the from one of its face, and W naught is the beam waist at the left face, for example, of the active medium rod, and WP is actually the beam diameter at a distance Z within the active medium rod. Eliminating, now you see that we have average value of RP expression in equation number 6 and 7. For example, from equation number 6 we have this expression, and from equation number 7 we have this expression. Now we can equate these two expressions and can solve for the value of the P threshold. So the pump threshold value, that is the P threshold, is equal to gamma over eta P multiplied by H nu P divided by tau, and then multiplied by pi into, within parentheses we have omega naught square plus omega p square, and divided by 2 sigma e. As the W naught, you see that when we focus the beam waist is formed there. So after the beam waist, the beam will diverge out. So as W naught increases, you see that since we are talking about the longitudinal pumping, it means that we are entering the pump beam from the left face of the active medium rod, and the beam will expand as it travels through the active medium through the length of the active medium rod. So as W naught increases, the field expands, a part of which lies outside the active medium region, and to maintain the threshold population, the threshold must increase, which is obvious from equation number 8. So you see that when WP will increase, then of course the P threshold has to be increased. So we need to consider an increased value of the P threshold value. So the P threshold will increase when your beam is diverging, and it depends upon the divergence of your pump beam that you are launching inside the active medium rod. The more diverged the beam, the more would be the requirement of the P threshold. So P threshold must increase, which is obvious from equation number 8. An equivalent relationship for P threshold for the transverse pumping case can be obtained by replacing equation number 7 by the transverse pump rate given in equation number 17. So you see that here in equation number 7 we are using this pump rate for the space dependent case, for the longitudinal case. But you know that now we are going to discuss this. We want to write down the value of this expression, that is the value of the RP for the case of transverse pumping, transverse case. And you know that in the transverse case, what we have to do is that we do not enter the pump beam from the faces of, from one of the face of the active medium rod, but we pump the beam transversely to the active medium rod, that is that is perpendicular to the surface of the cylinder. And if our active medium rod is in the cylindrical form, in that case the transverse pump rate, which can be obtained, which can be seen in the previous slide, equation number 17, this can be written as that is the threshold value for the pump rate, the average threshold value for the pump rate for the transverse case is equal to eta P into P threshold divided by H nu P, and then you have 1 minus e to the power minus a square, and divided by W naught over square root of 2, the whole square of this quantity. And this denominator, and the denominator contains pi into a square into L, where L is the length of the active medium rod, and A is actually the A is actually the dimensions of the Gaussian beam that we are launching at the cylindrical face of the active medium. And for the detail of these parameters, you can consult slide number 102, equation number 17. Now you see that we have these two expressions in front of us in equation number 6 and in equation number 9. So in equation number 6, the pump rate was defined generally by equation number 6, and you know that for the transverse case we have defined the pump rate as given in equation number 9. So we can similarly eliminate the pump rate from these two equations, and we can solve these two equations for the P threshold value. So the pump threshold value for the transverse case is given in equation by equation number 10. So P threshold value is equal to gamma over eta P multiplied by h nu P over tau into sigma E, and then multiplied by pi a square divided by 1 minus e to the power minus a square divided by W naught over square root of 2, the whole square of this quantity. So this is the threshold value for the case of transverse pumping. You see that again in this equation we have a dependence upon the value of W naught, where W naught is the waste of the Gaussian beam that we are launching at the surface of the cylinder. Again, as W naught increases, field expands, because you know that W naught is the minimum size of the beam spot, of the Gaussian beam spot, which is launched transversely to the surface of the cylinder, to the surface of the cylindrical active medium rod. So again, as W naught increases when it enters into the active medium rod, field expands, and a part of it now enters the cladded region of the rod being pumped. So you see that if our active medium rod has a cladding on it, and we are pumping in the uncladded region, then of course when the beam W naught will expand, it will also be intercepted by the cladded region of the pump beam, or by the cladded region of the active medium rod also. This demands increase in P thermal. So in that case, we have to increase the value of threshold pump power to maintain the required critical threshold population. So you see that this is because of the cladding. So if the cladding is there and our W naught is increased in such a way when it enters into the active medium rod, that a part of the beam is intercepted by the cladding by intercepted by the cladding, then of course the pump rate will be, the pump beam is reduced effectively, because some part of the pump beam is being intercepted by the cladding, and in that case we need to increase the threshold pump power to maintain the required critical threshold population. If the rod being pumped is uncladded, an aperture can be used to limit the dimensions, such as W naught could be less than equal to 0.6 times A, where A is actually the total width of the Gaussian profile. So that the field U remains unaffected. So you see that if our field is if our active medium rod is uncladded, we are imposing these conditions on the beam waste of the Gaussian beam being focused at the surface of the cylindrical rod, that is W naught should be less than equal to 0.6 times A, so that the field U remains unaffected. Because you see that we want to keep U unaffected, because this analysis is being presented under the condition that U should remain U should stay unaffected, and for that we are imposing this condition on W naught. The exponential term becomes insignificant. Let's consider the exponential term, this term you see. So here we are imposing a condition that W naught is less than equal to 0.6 times A. And you see that here we have 0.6 times A, and we are dividing it by square root of 2. So this quantity becomes smaller. And when we divide this quantity with A square, so this quantity becomes much larger, and due to the negative sign, it becomes nearly approximately equal to approaching 0. So we have a 1 minus 0. And then of course we can get rid of this exponential term. So under the condition that W naught is less than equal to 0.6 times A, so that the field u remains unaffected. The exponential term becomes insignificant, as I explained. Thus, equation number 10 for the uncladded rod case takes the following form. So the P pump threshold value for the uncladded case is equal to, you see that here we are discussing transverse case, so remember, so this is the P threshold value for the uncladded case, and for the threshold for the transverse case is equal to gamma over eta P multiplied by h nu P over tau, and then multiplied by pi a square over sigma E. So this is the expression that we have derived for the transverse threshold pumping case for the transverse case. And we have uncladded rod, you know that. So under that condition, we have used this one. So in order to keep our field to stay the same, unaffected, we are imposing this condition on the beam waste, that the beam which is entering into the pump into the active medium surface, so that the field stays the constant. Now you see that we have, I have presented, you see that this threshold value, two threshold values have been presented. One in equation number 8. This was for the case of a longitudinal pumping. Threshold value for the threshold pump value for the longitudinal case. And here in equation number 11, we have the threshold value for the pumping case of the uncladded case. And this is the general case, you see that, transverse pumping, general case, is given in equation number 10. And then you see that we have we have discussed the cladded case and the uncladded case, and for the uncladded case we have modified this formula given in equation number 10, and we have written this expression. Now you see that we are going to discuss further in detail about, let's see what we are going to discuss in next paragraph. In the 4-level laser system considered above, the lower laser level, that is the level number 2, was empty, whereas the lower laser level, that is the level number 1 or the ground level in case of 3-level laser system, is never empty. You know that in the 3-level laser system, our ground level becomes the lower laser level. But you know that in 3-level laser system, the level 1, which is the ground level, is not empty, and its population must be considered in the derivation of the threshold pump power. You see that in the previous results, when we were discussing the 4-level laser systems, and we were discussing the threshold pump power for the longitudinal and for the transverse cases. For the 4-level system, we didn't consider the population in the lower laser level, because the population was in the lower laser level was 0, or the lower laser level was empty for the 4-level laser system. But you know that in the 3-level laser system, the lower laser level is never empty, and we have to take into account the population of the lower laser level if we want to find out a correct formula for the threshold pump power. In an ideal quasi 3-level laser system, pumping process transfers the active medium particles to a third level, from which the particles are immediately transferred to second level, the upper laser level, which consists of many strongly coupled sub-levels with a total population of N2. Since in the 3-level system, the level pumping is run to level 3, but the level 3 immediately decays to the level number 2. So effectively, our upper laser level is the level number 2. And in the upper level, laser level, which is the laser level number 2, and the levels in the sub levels in that level are strongly coupled. So, and that forming a total value, say, equal to N2. Level 1 is the lower laser level, with which consists of strongly coupled sub levels in thermal equilibrium with a total population equal to N1. So now we have level number 2 and the level number 1, both level, all the sub levels in the level 2 are coupled strongly, so that the total population becomes in all such levels is total population is N2. And similarly, the level 1, all the sub levels in the level 1 are also strongly coupled together, forming a total population equal to N1. So you see that here we are specifically discussing the case of a 3-level laser system. When the net gain of the system becomes equal to the net loss, the population of the upper laser level and the lower laser levels are regarded as a threshold or critical population. For the space dependent case, we need to take the average values. So we have sigma E multiplied by the average value of the population in the N2 level, which is just the threshold value, and minus sigma A times the average of the threshold value in the N1 level. This whole term is multiplied by the intensity I, and then that is equal to, on the right hand side we have the gamma. And you see that we have gamma, we have already introduced gamma in the appendix also, that gamma is actually the logarithmic cavity loss, and capital I is the intensity of the beam. And then we have these quantities where sigma E, for example, sigma E is the effective value of the stimulated emission cross section, and sigma A is the effective value of the stimulated absorption cross section. And you know that we have multiplied these two, we have subtracted the absorption term from the stimulated emission term. So this is the stimulated emission, and this is the stimulated absorption term, and we have subtracted this term, and we have set this term equal to the cavity loss, because here we are saying that the net gain of the system becomes equal to the net loss. The population of the upper laser level and the lower laser levels are regarded as a threshold or critical populations. And under the critical or the threshold populations, we have written equation number 12, and we have set this difference equal to the logarithmic of the cavity loss. So where the spatially averaged value n threshold is defined as the average value of the n threshold either for the level number 2 or for the level number 1 is given by integral over the volume of the active medium contains n, the population in that level, multiplied by the absolute square of u multiplied by dv, and then divided by the integral over the volume of the active medium rod contains absolute square of u multiplied by dv. So you see that if we perform this derivation, if you perform the calculation on the right hand side, we can get the average value for the threshold value of the population in that particular level. For example, if we use 2 over here, we shall be calculating the average value in the level number 2, and if we are using a subscript 1, for example, as in this case over here, we shall be calculating the average value for the threshold case in the level number 1 of the 3-level laser systems. For ideal 3-level laser system, the population of the third level is 0. As we said earlier, that the population in the third level is almost 0, because this level decays so quickly that all the populations is compiled into the level number 2, which could contain many sub levels. So our total population, so N2 level becomes our upper laser level in the 3-level laser systems. So then we have that is the population in level number 1 plus the population in level number 2. Then the total population becomes equal to NT, because we are assuming that the population in N3 is almost 0. So you see that we can thus define for the space dependent case, we need to take the average values of these quantities. That is the average value of n1 threshold plus the average values of n2 threshold. These two values will add together to give you the total number nt, as shown in equation number 14. So you see that we have n1 average, we have n1 threshold average, we have n2 threshold average, and you see that we have these two quantities also over here present in this expression in equation number 12. We can solve any of these one. For example, we can here we have solved these two equations, that is equation number 12 and equation number 14, for the case of n2 threshold, average value of n2 threshold, which is equal to gamma plus sigma a into nt divided by sigma e plus sigma a. The effective pump rate is then given by, so the average value of the threshold pumping rate is equal to the average value of the threshold population in level number 2 divided by tau, where tau is the lifetime of the level number 2. Eliminating N2 thermal, N2 threshold, not thermal, eliminating the threshold value, average value of the threshold in level number 2 gives you the average value of the pump rate for the threshold case is equal to gamma plus sigma A into NT over sigma E plus sigma A into tau, because we have substituted in this case the value of average value of N2 thermal, N2 threshold from equation number 15 into equation number 16 to obtain equation number 17. So you see that equation number 17 now gives you the general case of the pump rate derived for 3-level laser system. Now you see that we have also this expression which we have already obtained for the longitudinal pumping rate in terms of the threshold pump power, can also be written if we replace PPE with P threshold in equation number 12 of slide number 102. We can write this expression as, so the pump rate, so the threshold value of the pump rate, so the average of the threshold value for the pump rate for the case of a longitudinal pumping can be written as eta p multiplied by p threshold divided by h nu p multiplied by 2 over pi into w naught square plus wp square, this whole quantity multiplied by L, as shown in equation number 18. So you see that if you want to see the detail of this one, you can consult equation number 12 of slide number 102. So you see that we have equation number 17, we have equation number 18. We can equate with the left hand side of both of these equations can be equated to solve this equation for the value of P threshold. So the value of the P threshold for the case of a 3-level laser system, for the case of longitudinal pumping, is P thermal. P threshold is equal to gamma plus sigma A times NT divided by eta P, then multiplied by h nu p divided by tau, then multiplied by pi into, within parentheses we have omega naught square plus omega p square into L divided by 2 into sigma E plus sigma A. So you see that all these terms, all the parameters have been defined earlier in this slide. And you know that equation number 19 gives you the threshold value of the pumping, of the longitudinal pumping for the case of 3-level laser system. Now you see that if we are not going to discuss the transverse pumping for the 3-level laser system, because P threshold for the transverse case is much higher and is practically insignificant and worthless to report, because the value of this is so much higher that that any discussion will not make any changes in the value of this one, because this value is already very high for the case of transverse pumping. So a precise value calculation of this precisely would not matter, because the value is already has a very large value. So practically the calculation is insignificant and worthless to report. You see that for the case of completeness, we can give the value of the, for completeness, the threshold pump formula for the lamp. You see that if we are using lamp for the pumping mechanism, and you know that the lamp is used only for the transverse pumping of the active medium rod, and if we are using a lamp, then we can obtain the following two equations. And you see that this is for the completeness of this topic. We are also going to discuss the transverse pumping through the lamp of an active medium rod, and we can write the threshold value for the pump rate in case of transverse pumping using a lamp is gamma over sigma E into L into tau. And then you see that we have the average value for the threshold pumping for the transverse case using a lamp is eta NL eta PL multiplied by P threshold divided by H nu MP. You see that here I have written nu MP, that is I have considered only M stand for lamp. So this is the frequency that is from the lamp, and you know that a lamp is not operating on a single frequency. So here we are giving this relationship only for a single frequency of the lamp. But if there are many frequencies, you need to accommodate that thing also. And you know that this is multiplied by 1 minus e to the power minus a square over divided by the omega OL by the square root of 2, the whole square of this quantity. And you know that here we have written omega OL, which is the value of the beam, pump beam, using the lamp at the surface of the cylinder, active medium rod. So here you see that here I have used W0L, because you see that beam waste cannot be precisely defined for the case of an ordinary lamp, but you know that we can roughly give an idea. So this W0L is actually the radius of the radius of the beam, which is of the lamp beam, which is being focused on the surface of the cylinder. And here you know that this is the lamp frequency. So if since many frequencies are involved, you need to take care of all those frequencies, or you need to calculate for each individual frequency this expression, and then you need to sum up those in order to calculate to give you the average value of the pump rate for all such frequencies. You see that we can equate these two pump rates given in equation number 20 and 21, and we can write down the threshold value for the pump rate using a lamp. And you know that this pumping is actually a transverse pumping is given by the expression in equation number 22. So you see that we have given the expressions, we have given two expressions for the 4-level laser system. That is, we have given the longitudinal expression, and we have given the pump threshold pumping expression for the case of transverse pumping in a 4-level laser system. And then of course, and then in the case of a 3rd-level system, where we also took care of the population in the lower laser level, we mentioned longitudinal pumping and also the transverse pumping for the 3-level laser systems. And then you see that in the case of a pump in the case of the pumping by an ordinary lamp, we have given that expression also for the completeness, and this is given in equation number 22. So you see that this is the end of slide number 103.